Good afternoon everyone. Welcome to the educational tutorial titled Introduction to Simulations for Honours Students. Today we'll be going through a brief introduction of what computational chemistry can do for us before detailing how to install Material Studios, how to set up an account with NUS CSE, how to use Material Studios by going through some simple tutorials, and just to wrap up the kind of lessons we can learn. Now, computational chemistry is able to predict the outcome of experiments, and it's able to do it with a high degree of accuracy, and this allows us to prove various concepts that we may have. Now, using this diagram over here as an example, we can look at the absorption of oxygen on metal oxide surfaces. And what we see over here is that we can measure the bond length between oxygen and the metal, which is zinc. And we can also measure the bond distance between the oxygens, and this will allow us to gain some insights on the nature of the absorption, whether it's physisorption, chemisorption, and the kind of effects it has on the surface as well as the oxygen molecule that's adsorbed. Today we'll be going through a simple tutorial on how to study the absorption of acetylene on this tin oxide surface that is doped with antimony. Now let me give you a short video of what we would like to do. We would like to look at the reaction between this acetylene and the surface. Now I'd like to show you how to install Material Studios, and the first thing you would like to do is to start up your internet browser, go to Google and type in NUS HPC, which stands for High Performance Computing. It should be one of the first few items that you see from Google. Now, we would like to install the software, so we would like to scroll down until we see this item over here called Application Software. Click on it and it should bring us here. Okay, and we would like to scroll until we see Material Studios. Click on it and scroll, and you'll see this that says install MS Visualizer. Go to this website over here, download the file, and just click on setup to start the installation. Basically, that's how it's done. Alright, and next we would like to go back to Google, and this time around we'll key in NUS CSE because we would like to set up an account with NUS CSE. CSE stands for the Center for Computational Science and Engineering. Now click on it and go to access and login. Alright, so basically we'll need to create a valid user account. Just click on this link over here and it should bring us to a web page that details the kind of information that we'll need to send to this address over here with the following information. You've got to state very clearly what is the purpose for using the computational facilities. And after you do that, you should be able to get an account. Now, after installing Material Studios, we should be able to get here simply by activating the software itself. So, well, what I did is I went to File, I went to create a new project, and I titled my project as CM5198_recording. Okay, so following our tutorial, first item on the list we would like to do is to draw an acetylene molecule. So how is it done? To draw an atom, right, click this icon over here. It says sketch atom and is by default carbon. That's very good for us. So acetylene is 2 carbon atoms. Alright, so we'll draw 2 carbon atoms. We'll change the display style to ball and stick, which is my favorite. Now, acetylene has 3 bonds between the 2 carbons, so we'd like to change this to triple bond over here. And we can apply, it becomes a triple bond. Now we'll need some hydrogens, so we click this button over here and it gives us hydrogens. If we have a more complex molecule, we tend to like to clean, using this button over here, and it helps us adjust the geometry of the molecule that we draw. But for this case, it's perfectly fine. Alright, so we would like to send this molecule for optimization by sending it to the CSE account that we have. And let me just fast forward you and show you the kind of results that we'll get after the optimization process. Okay, this is the optimized molecule of acetylene, which looks very much similar to what we just had. The difference we can see is that there is this button over here, they're activated. So we can actually play and see how the software actually optimizes the molecule itself. So now that we have the acetylene molecule that is optimized, what we'll do is that we'll need to have a metal oxide slab for us to perform the reactions upon. So what I do is I right click, go to new, I create a folder that is titled bulk tin oxide, and I go to this folder over here, right click again and press import. Okay, I look into metal oxides and I search for tin oxide SnO2. Okay, this is the unit cell for bulk tin oxide. Alright, and here we would like to cleave the surface because we would like to have the surface of tin oxide. I choose the 100 plane, I cleave it. Alright, and I look at it and I think, well, 4 stoichiometric layers of tin oxide is pretty good, for example. I'm satisfied. So what I do is I'd like to enlarge the surface. So I'd like to make a supercell out of it, make it bigger. Alright, so I'd like to have say 3 times of V direction and 2 times of U direction, and I create this large cell. Alright, so now that I'm satisfied, I'd like to create a vacuum slab so that I can impose the periodic boundary conditions. So now it looks like this. Alright, so let's make the display style ball and stick again. To me that looks nicer. Alright, so what does periodic boundary conditions mean? What it means is that over here the lattice, right? Let's say we multiply it many times. Periodic boundary conditions means to say that this particular unit cell is repeated in the X, Y, and Z directions. Alright. Okay, so now that we have the surface of tin oxide, I would like to study the surface reactions of doped tin oxide, for example. Okay, so how do I do it? If I like to dope this tin oxide surface with antimony, what I'll do is I'll click on this particular metal atom that I would like to change, click on composition, click edit, click this button over here, and select the element that I want. I want antimony. Alright, so press OK. Now you'll see that the color changes to antimony. Okay. Next, to perform the surface interactions between acetylene and this tin oxide surface, what we need to do is, as per normal, we will need to send this particular surface model for optimization. After that, what I should get is, I should get the optimized surface. Is something that looks like this. Once again, we can take a look at the optimization process. So we see that there is some surface relaxation over here at the top. Okay, so now I would like to perform the interactions between the acetylene and this surface. Alright, so let's just label it as reaction. Okay, so what I'll do is I will copy this surface over here, paste it over here in this new and empty file, go to acetylene, do the stain. Alright, and I'd like to adjust the molecule so that I can start off with a relatively reasonable state of adsorption. Okay, so what I like to do is I like to target the interaction between this carbon and this oxygen, and this carbon with this oxygen, as shown in the video just now. Okay, so now that I have this and I feel satisfied with the geometries, I will send it to CSV for optimization, and what I should get is something that looks like this, for example. Alright, we can look at the optimization process. So what we see is we see this molecule moving upwards. So this is the optimized structure of a physisorped acetylene molecule. Alright, and by tweaking a little bit, we can see we can obtain a chemisorped acetylene molecule on the surface. Okay, so now that we have a physisorped model and a chemisorpted model, we can look at how the reaction moves from physisorption to chemisorption. Alright, so we set up this reaction preview over here. Now we have a reactant. That's the reactant that we have. Okay, and this is the product, which is the chemisorpted acetylene molecule. So now we'd like to make use of a function in Material Studios, which is the reaction preview. Okay, reaction preview. So we can select the model that we want. We want our reactant to be reactant, and we want the product to be a product. Okay, so now we will need to match the atoms together. Now I've already matched the atoms, so let me just reset this and we can rematch them all again. Okay, so the first thing I'll suggest you do is you close all of the windows, and I'll go to reaction preview again, select them, match. Now this time we can use auto find, in which the Material Studios would match for us automatically. We can try that again. So now we only have some very few atoms in fact to match. Now, so what we can see is we will see that this yellow highlighted atom is the hydrogen, and we want to match it with this hydrogen over here. So we set the match. See this carbon, we like to match it with this carbon, which is good. So we set the match, and now we look at oxygen. Yep, that is the oxygen that we want. And we will need to check this, turn this around, and yep, that is the oxygen that we want. So now we have a perfect match. So we would like to create this reaction preview, and you can preview this. The computer may take a while to generate this diagram, this video, sorry. So now change the display style, go to lattice, extend it in the B direction so that we can get to see everything. Alright, so the next thing that we can do is to just hit play, and there we are, there we have it. That is the reaction that moves from the physisorption to chemisorption of acetylene on doped tin oxide. Alright, so just to wrap it up, what we have learned is that computational chemistry is not difficult, although I would say that it's not trivial either. Modern computers have definitely increased the capabilities of the software, and we can do much more as compared to before. And I would suggest that you practice, and practice, because practice definitely makes perfect, gets you more familiar with the software, the equipment, and I'm sure you can do it very well. Alright, that's all from me, signing out.